So now let's talk about the design procedure, or the second type, I mean the second approach of combinational logic. That is called the design procedure. We said that we have a circuit, and this we have a Boolean function, and we want to drive it is, first of all, drive it is truth table, simplify it, the expression which we have, and at the end of the day, we will implement our circuit which it is required, because we are talking about the designing. So we have a mathematical things, or we want to construct it as a truth table. Maybe I will give you just like a K-map, numbers, simplify BOS, which it is like a product of sum or sum of product. Then you have to design your circuit according to the procedures which you have it. Let's take example. For example, if I take BCD to X's code 3. BCD, as I told you, that it is a number which it's from 0 to 9. Okay, so 0 to 9 means it is 4 binary bits. Because look, for example, here, let me just show you how. If I have it like this, BCD, it's A, B, C, D. There are, for example, 4 inputs are available normally there for BCD, because we are talking about from 0 to 9 means that the binary bits which I will have them from 0 to 15. But I am interested only about the first 9 bits, about the first 9 positions. For example, I'm interested about 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, about these. But the rest from 10 up to 15, I am not interested about them, as they are not in BCD. So if I have 2 numbers and I want to add them normally in BCD, they should be fall in the range of from 0 to 9. If they are out of that, they are 12, for example, 5 plus 7 or something like this, they are out of this range. So I can say that they are not a BCD numbers. So I know that it is a simple way representing the ABC or BCD numbers in binary bits. Just I will take the bit. For example, if I have the number of 12, suppose that I have a number of 12, for example. Like, for example, I have the number of 12. 12, what it is? It is in this is out of BCD number, right? But if I want to represent these 2 numbers in a type of BCD, just I will take this one here, this one here. Okay, remember, in binary bits, this it has its value 0. This one it has its value 0, 0, 0, 1. While this one it has 0, 0, 1, 0, 0, what? 1, 1, right? It will be like that. So sorry, it will be like this one, 0, 0, 0, 0. Okay, 0, 0, 1, 0. So this is representing the 2 bits. This is representing the 1 bit. This is normal in binary numbers. I mean, when I write it normally. But if I want to go, for example, for the BCD, I will say these 2 numbers here, they are representing the BCD, right? If in binary number, again, let me remind you that in binary number, one thing is there. In binary number, I have also up to for the hexadecimal up to what? Up to 12, right? How can I represent this in binary number? Anyone can tell me? It is 1100. You remember? If just you take from 0 to 15 and write it 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, I mean, you go. The 12th number, it will be front of it like this. So this is in binary number. Okay. In hexadecimal, I will write in BCD as it is fall out of the range of 9. Just focus on this. it falls out of the range of 9. So because up to 9, I can say BCD. Above that, it is very difficult. So what I will do, I will take this independent. I will write it as corresponding in binary bits. I will take the 1 and I will write it as corresponding in binary bits. And I will say, oh, okay, this is now a BCD, which is equivalent to the 12th number in binary. So if I have this number in binary and I want to write it, I will write it in BCD like this. You understand the things, or I have to repeat it? Hello?
Yes, sir, we understand.
Okay. Again, for the 12th number, for example, if I want to write it in simple binary numbers, I will write it because as they are 12 means that they are falling in the 4 bits, or it has a 4 bits. It is equivalent in binary bits, this one. If I want to write it in BCD, it's not right for me that to write a 12th number in BCD because it falls out of the range of the BCD from 0 to 9. What I will do, I will write it just like independent. This one and this one. So, and their combination like this will give me the BCD number. Now, this is not here our case. Just this, it was like showing you, I mean, the difference between how to write the binary bits for as a number and how it is represented in BCD for the same bit. For 12 bit, for 12th number, just we write it in binary and in the same time and in the BCD. But the question here, which we want to design, it was something else. He said, please design a BCD that will BCD, which will give me the result of X3. Why he did not give me, he did not, for example, say, which he give me the result of binary. If I go, I will just show you now here. Look, in binary normally, in X3 normally, what you have to do, you have, for example, if you have the first bit, the first inputs, you will add to it a 3. So this, when you add to a 3, you will get the same result, this one result. So 0, 0, 0, 0. When you come to add 3 ones, 0, 1, 2, 3, it will give you this result. This result will be here. Understand? Hello? 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 Okay.
Yes, sir.
No one, I think all of them, they are away from their phones or something like that. Anyhow, okay, now you will have it like you will add 3 and you will get these results. Now look here, we are using X3 because if I add any number, any one, I mean of these, just I subtract it from 9 because I'm saying about the BCD converted to X3. Any number, 9 BCD means up to 9 minus any number. Just if I say any number. Okay, so if, for example, I take this number, the first number, and I make it minus 9, what will give me? It will give me the complement result or the inversion result. If you can see, compare between this and 9, 1. Only the inversion to that. Here 1, 1, here 0, 0. Here 0, 0, here 1, 1. Okay, let's say, for example, I want to make another one. I don't know if people are available or not. Let me, for example, talk about the other one here. If I take number 4, for example, or any number, for example, I take this number 0, 1, 2, 3, 4. For example, this, I take this one. And I subtract it from 9. 9 minus 4. What will give me? It should give me also the complement of it. Look, the next one, what will be? 0, and instead of 0, it will be 1. And the result here, what will be the result? 0 minus 4 will be 5. So the 5 is the inversion of 4. Okay, same result in the previous one. 9 minus 0, it will give you 9, which it is the inversion of the first column. You understand the point or not? Hello.
Yes, sir.
Okay, focus again, please, with me. Again, if you have, now I'm talking about this. If I have any bits, if I want to transform my BCD to XS3, it is simply that I will just I will put in my mind 2 or 3 steps. First step is that BCD, BCD basically they are how much? They are 4 bits. So it is from 0 to 15. But I am interested about from 0 to 9 only, from 0 up to 9. That's what I'm interested about, not anymore. Okay, the other ones I can consider them as don't care. Okay, this is first step. Second step, 4 inputs here, I will have 4 outputs here. 4 outputs here means that for this one I will have 1 K-map, 1 circuit, 1 Boolean function, and this one 1 K-map, 1 Boolean function, and the same thing I will have for these. So for every one of these I will have it is K-map. The third one, why I am doing XS3, not I'm doing a binary number. If I am going to design a binary number from BCD, means that I have to implement a circuit for each input, which will make the things for me more complicated and more complex and difficult. The best way is that just I will use XS3 so as the output of the BCD. So in case I have, for example, because why I'm using this, XS3, they have a very simple formula, say that just you subtract the given output from the one of these from the what? From 9, which represents the BCD maximum range. So if, for example, I'm going to subtract the first one, this is which it represents 0, 0, 0, 0. What will give me? It will give me the 0 prime and the 9 prime. 9 prime means the complements. It will give me the complements of 0. I can say like this. In other words, either it will give me 9 or it will give me the complements of 0. Okay. So look, this represents 0, 0, 0, 0. Okay. What is the complement of it? 9, 1. This one. And instead of 0, 0, it became 1, 1. Then 1, 1, it became 0, 0. Let's take another example. For example, if I take here a bit of, for example, 5 or 4, for example. If I take 4 here, what I will get the result here? The result here is 5. So this 5 should be the complement of 4. By this way, it's very simple for me. I mean, if I have construct half of these tables, I will just go and, without doing any mistakes, I will subtract from 9. I will subtract the values from 9 and I will get my result. Look, this is 4, for example, 0, 1, 2, 3, 4. This one. This is here. Now, this is the value of 4. What the result was? This one, 5. Now, if you see 5, it's totally the complement of 4. And instead of 0, it became 1. And instead of 1, 1, 1, it became 0, 0, 0, and so on, until you reach the 9 one, the last one. After that, you will say, I don't care about anything. I mean, it's not a big issue for me to just, I will fill it with the x, which it is the don't care functions. So what I have to what I have to understand is that the inputs are 4 bits from 0 to 9. The output is 4 bits with the value plus 3, which it is the excess code. Okay. Look here. Now, for the first input, for the first output of these, which, for example, it was W, I have it here. Now, what was the result when I compare these, for example, here, now I take first all the outputs from here, the inputs from here, for example, this is the first one, then I have to take this one and I give it again another 3 bits. What I will get this value plus 3 bits, I will get this value and so on. Now, when I construct my table, this one, this is called W, or as we call it before, F. I mean, it is the function, which here it is represented in this one. So I have to build it as what? A, B, C, D, because they are like 4 bits, 4 inputs, A, B, C, and D. They are here. Okay. So now I will fill the values where ones are there. If I can see the first 5, 0, 0, 0, 0, 0, 0, just I will make it here 0, 0, and 0, then 0, then 0. This here. Or let me make it in another way. It is in this table, even more. It can be more clear for you. Now, the rest one is 1, 1, 1, 1, 1. So 1, 1, 1, 3. Then I have to shuffle and go to the second last, and I put 1, 1, because this represents here M8, M9, M10, M12, while this one representing this curve, this row here represents what? M12, M13, M14, and M15. So if you can see from here, now we have until 9, right? The values with us until 9 only. So until 9, but after 9, I will write don't care condition. X for 11 and 10, then for all these, I'll just write don't care conditions. That's it. I mean, this is the way which I am manipulating and doing my circuit. Look, my K-map. Now, what I have to do after that? After this, just I have to build or to minimize, according to the 3rd chapter, minimizing my what adjacent squares, or minimizing the ones, or minimizing the gates. So here I have 1, 1, but the rest are don't care conditions. I will take all of them as 1. I can take all these as 1 value. So when I take all these here, what I will be here, if I can see A is constant, A, this value and this value, while B is changing, so B will be removed. And the other bits here during, CD, here and here, and during all the columns are changed. So I will be just with the value of A. This is the visualization power which I was talking to you. Just when you see your circuit, you minimize it easily. You will see the fixed one and you will write it. The one which varies, it is results from one to the other adjacent columns, or between the columns and rows, you will remove it. Here B, it is from this point to this point has been changed, from this row to this row has been changed, while A is fixed, so A is written here. B is changed, means removed, because when it's changed, it gives me B and B prime. Here again, CD changed during all these, because I'm talking about all these circuits here. So here, don't care condition became beneficial for me, that it reduced the input variables and the literals. So if you come for the other one, BCD, if you take, for example, this one here, because here I have 1, 1, and we say that the adjacent, I can't take the adjacent squares, but I cannot take, like odd squares. I will take the even ones, either 2 or 4 or even whole. but not the evens 3, 5, or 1. So these two, when I want to take them, I can take them with another also two care conditions here, or two don't care conditions here. Then from this, what I will get benefit, B will be fixed while A is changed. B is fixed while A is changed. Okay, what then will be? Here, what also is fixed? C is fixed, if you can see, but D is changed. What I will get then the result? I will get BD, this one. And the third one, just I will square these two. I will take them together. I will group them basically, not square. I'll group these two squares together. So, and I will get this result. So the first output will be W, it's equal A plus BC plus BD by constructing it is K-map and finding it is Boolean function. Now, come for the other one, for X1, for example. For the X1, you will get this result. Here, same. What you will do, this is 0, 1, 1, 1, 1. You will write it 1, then 1, then you will come to this 1 and 1. And then you will go through until the last one, which is number 9, and you will put 1. The rest, after 9, you will fill it with don't care conditions, which is this one, 11, 10, 11, 12, 13, 14, and 15. These are don't care conditions, which I am not interested about them, but there might be a beneficial for me to minimize the Boolean function. And just when I have them like this, I will group these two together. I can group it. I can group this one with one of the don't care, and I can group these two bits here with two of the don't care here. And at the end of the day, I will get this result. Similarly, if I go for the Y function, which it is this one, or I go for Z function, which it is here. I mean, just what we have to do, you have to be careful about this example. This is like a practical example, and might we do it in the lab, or I don't know if you are going to do it, but we have to discuss that. The main important thing is that when you convert your binary bit BCD to XS3, you have to put 4 values, 4 inputs, I mean, then you'll get 4 outputs plus 3, which is the access code, bringing the access codes for that. Then you have to check the inversions and or the complement of each number. Complements already, which you have done it in chapter 1. Just if you have, for example, and as it is BCD, so the maximum one, it was 9. While, you know, you remember that we have done the complements of 10, how you take the complements of the 10 complements and also 2 complements. Then you have taken also the 9 complements and the second one, which was the 1 complements. Now all these which you have, those which you have studied before, it will come through you again and again. Let's see now when you construct your truth table, I mean in more detail. Just you write a value again until 9, and the rest of them for X, Y, Z, you will just fill it like this. X, 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 X until 15. Okay? Now, and this is here again, like what I have explained for W1, just when you group them together, you will get this function. For also for the other one, when you group them together for the X, you will get this function. And for Y, when you group them together, you will get these functions. Already we explained it in the previous one, but in more detail, here you can see how the, how the combinational or how the grouping is going just through the PowerPoint, or when we use it, I mean, for more clarification for your people. Now, let's come for circuit. We finished that. This is the thing which just aim in designing circuit, we have to design the circuit which we were talking about. The circuit which it has 4 inputs, A, B, C, D. Excuse me, do you hear me or not? Okay, this is the last one. I'm not going to make more because I know that people, they are not.
Yes, sir.
I don't know if you are interested. I will go through. I mean, I will cover as maximum as you want. If just you want me to stop after this example, I will stop after that, and next time we will carry on, whatever you like. Okay.
Okay, sir. Okay, sir.
Let me finish now. Let me finish the design procedure. Already we have designed this one, and we have found what is W, what is X, what's Y, what's Z, which they are here now. But, and this is are the input. According to my table here, I can just implement my circuit. For example, for W basically what it is? It is A, this is A, and then it is B when it is ORed with, when it is NAND with the ORing C plus D. Just you have this is B here, and where is C? This is C here. When you OR these, like for example, this C here, you will OR it with what? You will OR it with this D. You got the point or not? Hello?
Yes, sir. No.
This is C and D, right? What you are going to do, you will OR them. So this is C here, and this is D here, right? So this is the result now of ORing one, okay? So from here, you have to AND this one here with whom? With this P. According to this formula, I'm talking about this. I'm talking about this formula here. I'm talking just about this one, okay? You have to OR it with this one. You have to AND it with this one. Now, the result, what you have to do, you have to OR it with, according to the formula here, you have to OR it with A. Should I repeat it?
No.
No, sir.
It's clear?
Yes, sir.
Yes,
It is clear.
Okay. I know that it's not clear, but okay, people, I know this.
So you can put in too.
I know everything, yeah. Okay. One day I have been a
Sir,
student.
you are very genius. Sir, you are very
pass
genius.
through this. So that's why I want you to understand the things I mean. This is the thing. Just if explained only one of them, the rest you will understand it. So we will explain only this example, and we will close this session. Okay, let's talk about the other one, which it is like, for example, I want to find the value of Y. This one. Okay. So what is the value of Y? C plus D, but both of them, they are complement. Okay, so I mean they are prime. So this is D prime from here, right? And the other one, but when they are both of them, they are complement, means that I can first add them or them, then I give them the complement. C plus D. This is C. This is D. 1 minute. This is D, and this is C. Okay. Now I pass them through the prime one. This one. Okay. I prime them. Now the result of them here, what will be? It will be added here with what? With C and D. This is D here now, it comes. And this is C, so it will be added here. So the result will be C plus D prime after priming. This is the prime for their results, plus C. Okay. Who will do for me Z1? Hello?
Yes, sir.
Yes, who will make the output of Z?
I will, sir.
Yes, please.
Sir, here or on class?
No, here.
Okay, sir. Uh, sir, here is not get only one bus.
Sorry?
D not.
Yes,
Sir, here is D complement
bus.
and
That's it. Yes,
D is
this is
connected
it.
to not get
Yes, just you.
inverter.
Yeah, you have D, you will pass it through the inverter and you'll get Z.
Yeah, it's
Okay?
very simple, sir.
Yeah.
Sir, you
So,
should ask me a difficult question.
aha, we have hero here, huh? Okay, I will ask. Okay, but in the class, inshallah. Okay, now I
Sir,
think.
solid 1 marks. Sir, solid 1 marks.
Okay, okay, remind me in the class. Okay, okay, now it's finished up to here today, the lecture. So next time we'll talk about the half adder and full adder, I mean the binary adders. And thus you have to enjoy and go for your take rest. And please, can you write me the attendance, Qamar? Hello? Hello?
Yes, sir. Yes, sir. Yes,
Yeah,
sir.
can you please screenshot the attendee people? The present people, just
Sir,
screenshot.
let me. Sir Abdullah, Adil, Sham, Arfa, Iza,
Just
Hana,
screenshot.
Sirat,
Make
Sida.
screenshot for that.
Okay, sir.
Okay, and
Sir, everyone is present.
I will check them again once. Okay, brother. Then thank you so much.
Okay, sir.
So I close. Okay.
Okay, sir. Allah Hafiz.
Okay.
Have a nice day.
Have a nice day. Have a nice day.
Happy weekend. Allah Hafiz.
Allah Hafiz.
Goodbye.